I try to join when I have time or share with the community. There is a lot of interest on this activity, and for me to participate is a great pleasure. This is the photo that the workshop sent on the announcement, and I'm very glad that they chose the photo. I didn't choose it, and it shows a little bit about what we're talking about the youth, which is the students that are coming behind us. I wish I could be a student forever, but they are the youth. They are the ones that are pushing very hard, and they are coming with new ideas. And I think this is the work that I present, the ideas of my students and their vision about the next 10 years, 20 years, which I think is what this workshop is encouraging. So I applaud the organizers for this activity. The bridge that I have here is in Colorado. It's from our campus, and this is the tallest suspension bridge in the world, because it's the canyon is very deep, so that's why it's the tallest. And it was designed by the father of Ralph Peck, the famous civil engineer. And this is the group and some of the activities that we've done recently. This was last month. The group has grown, and we had a conference where the young researchers, the students, undergraduates, and we also invite high schoolers in my group to come. And we also invite seniors. There are also people from industry that are very interested in activities like this workshop, so they can recruit the future leaders of SHM. So again, congratulations for the workshop, for doing these activities for them. Some of the highlights of what I'll be talking today, as Christian mentioned, augmented reality, this frontier between the human and the data that we are collecting. We are looking into human factors about understanding, cognition, training, learning, real-time response with not of the actuator, but maybe the human is the actuator. This is a time machine measure that postdoc Yachi Shu developed with Jack and Elijah, where you can travel on time and you can see the evolution of your structure. It could be a disaster. It could be also some maintenance activities. The tasks that typically we develop are industry center. As Christian mentioned, some of my experience 10 years working for the private industry. So we identify that the owners are very interested in SHM. Not only railroads, but also any transportation or energy industry. We are doing some construction inspection and also some low-cost sensors that we even put on rockets. That's very exciting because in civil, things don't vibrate too much. So we need to collaborate with other activities. I know Professor Chatzi is doing a lot of things with wind, because the wind is creating some vibrations, and that gives us the opportunity to have a strong connection between our theory and industry needs. With the national labs here in New Mexico, we are very lucky. We are working with Sandia National Lab, Air Force Research Lab. In particularly, some of the work that I present here today is with Los Alamos National Lab. They are a little ahead in terms of dynamics. We're doing some nonlinear dynamics that I never thought I would be investigating, and we're looking into these multiple input, multiple output areas of interest. With the Navy, we have some support or ongoing efforts related to the cybersecurity of SHM. So when we have all these sensors, I'll be talking a little about community center SHM. How can we protect from attacks that are not only physical, but also cyber attacks? And here, in terms of augmented reality, I'll show some of the work that the students are doing. One is on dynamics, other work is in cracks, and the other work is in sensors. So let me bring this down. So we have some interesting work with the students in mechanical, actually. So that's why I need to get this cross-appointed. In order to be mentoring students in other departments, they recommend that you become cross-affiliated. So the University of New Mexico encourages this multidisciplinary participation. So let's get at it with the outline, SHM, community center SHM, then we'll talk about the human data interface and augmented reality and conclusions. For the infrastructure, all this decay or these maintenance concerns or repairs in America, we have the American Society of Civil Engineers. They have the community with the government, where we go and talk with the senators, and with the senators we talk about giving a grade, and actually the senators say this report is the most useful tool that they're receiving in Congress for asking for money. So what we do is we give a grade, and we explain in a very short, simple report the grade that they get, and then they can fight for improvement on bridges and structure. So using this, you can see the score is C-, not very good from last year. And the way in industry we take care of these low grades is by inspection. So some of my work was dedicated to inspect bridges when I was in Illinois. I was one of those little bats hanging from the bottom of a bridge, regularly looking for changes. So the core of this presentation is not replacing the human, but helping the human. So the humans are good, the humans are experienced, the humans have knowledge, and we want to support the humans that are doing that great job of inspecting bridges. It could be other structure. So today, if the humans are the one collecting this data, let's help those people who are doing the job. Let's help those who are leading this job, which are the inspectors. The SHM community, we are working closely with them. I have a little video here. Let me see if I can lower the voice for the sounds. And we are collecting data from many ways, not only sensors, but also doing some robotics, instrumentation, and drones. And stemming from here, let me, we have information. This is some of the work that we did at the University of Illinois near Chicago. Chicago is the hub of the railroads in North America, where with these sensors, we can obtain real-time information of the loads, the direction of the train, the speed. In this case was an Amtrak train passenger going northbound, 80 miles an hour. I forgot to close the box, so that's why you see the vibration of that wireless sensor up and down under the wheels. That makes it look very cool. And with the strain, with the 45 degrees, we can obtain this information that will inform us of the safety, maybe improve management of the traffic, and also if it's if you want to coordinate with the maintenance operations, you base on data. So this is what we've been doing for a few decades now, and we are very successful advancing the topic. But one of the challenges have been that interface with the community. Some of the solutions that we found with the assistance to sensors is developing low-cost sensors. This is an approach that we do here at the University of New Mexico. We call them low-cost efficient wireless intelligence sensors. And we tell them, you know, it's not that expensive, it's not that complicated. And also we can change the sensor for you. So instead of telling them what do they have to measure, we ask them, what do you want to measure? And then we fabricate the sensor for you. We allow the community to tell what do they, if they're interested to measure, and we will do it for them. We also use it for teaching. I just wanted to shout out to the students, and we have a class in civil engineering here where we teach a sensor. Professor Chatzi is aware in the International Model Analysis Conference, we do the teaching of the sensor. So maybe next year, if you want to take this sensor class, you can build your sensor in half an hour and use it and see the data. This is, look at the students, how happy they are when we build this low-cost sensor. In this low-cost sensor, the community now, they're not worried about you're gonna charge them a lot of money. And also you can tell them, hey, if you're interested in environmental issues, we can also change the sensor for you. This was work conducted with NSF and the Navy, and we developed this new generation of sensors. This was done by Joshua Murillo, and as you can see, it's a very, very crowded, busy box. This was the Lewis 5 sensor version A, and let me see this here. Okay. And then we have interest in putting this on the out there to collect this remote sensing that we have for the community. As you can see, it's a good it's a good design. As you can see, you have some of a level of organization, but we identify, we also have camera, sensor, water, turbidity. But here you can see it was a little room for improvement. So we did a version 2 based on the concern of the owner, and we developed a more advanced low-cost wireless sensor here, where it's 3D printed, and we had this was done by Solomon. And as you can see, the new generation is so much better, so much better. So the community, again, tells you what to do with the sensor. When you allow them to criticize your sensor and you fabricate it again, you empower their understanding of your technology. So that's being one area of value. In North America, with the history of our recent history of our collaborations with Native Americans, we identify there is an advanced knowledge in the environment on our partners. And we have a project with the Smart and Connected Communities where working together, community-centered research enables the adoption of technology. And that's what we've done here with the OK Owingwe in New Mexico. They are the ones who informed the sensors. When we told them we wanted accelerometers, they say, hey, we want water levels. So that's what we did for them. We developed a low-cost sensor where they can measure the flooding on real time. They can use it also for emergency planning. And also they have these fragility curves where they can use the community-informed decisions. So basically, instead of you telling them what they have to do, they tell you what is the framework that they want us to develop. Because they're very interested in the respect of the water is sacred. We protect our deployment with cybersecurity. This is some of the locations, and also we are investigating coding the cybersecurity with Tewa language. And as you can see, some of the signs that we have there are also written on Tewa. This is linked with High Water Mark, which is a private company, and Filiswina, who is the leader on this area. And some of the locations, this is over the Rio Grande. This is the interface where we have this, as you can see, these water sensors shooting down to the Rio Grande and collecting the change of water. And we have this interface where you can see the water. This was a couple of weeks ago. So very successful in the community intervention. Let's scale down this trust in data to the human level. And I'll show you why this is important. When you have this structure, when you have this inspector and you're talking about the real-time visualization, if the inspector don't see the sensor data in real time, they don't trust it. Also, the database being modified with this sensor data has to be, that's what they want to use for decisions or maybe liability. So they want to use it for management. They want to do decisions on real time. So those are the challenges that we identify with the human inspector and our sensors. So we're trying to, in the event of an emergency, it makes very clear why the human infrastructure interface is important. If you want to rescue people or you want to change some timely decisions on a disaster, you need to share that data and have the ability of the human to change that data on real time. So this automation helps humans to better interact with their environment. So it's not, the data is to help humans to interact with their environment better. That's what we're trying to do. So this is a very short video about how we build this thing. This is some of the 3D printers where the students are creating these hundreds of sensors that they do for the OK Owingwe. This is our little approach to this. This is the teaching of the class where the students build the sensor in 30 minutes. Again, you can see some of the Navy guys there teaching the class. These are some of the building against the clock. When you build sensors in half an hour, you trust the data of that sensor on that same day. So we are changing the fear of civil engineers to sensors by actually teaching them to do it. This is in California on one location where we have the The Navy wants us to measure the water level on the sea instead of the Rio Grande. No problem with that. And this is an upcoming effort. We're gonna do augmented reality above and below water. This is the chasing of the underwater vehicle with the boat. We have some of our sensors mounted on the boat. This is also, we're looking into human machine interface, maybe the quality of the interface below water. And this is some of the, at the end of the presentation today, I'll show how we can conduct safer inspections out there on the mountain near the Los Alamos. The data that you see here on the screen is programmed with augmented reality. We do everything with Unity. So we not only build the sensor, now we're building we program everything on Unity so the inspector can see the displacement in front of them. This was done during COVID. So in reality, we are not on the field. So this is in the apartment of the student. The train is inside the apartment, is moving right and left. And with this movement right and left, we can change the decision. The decisions that we did before was the speed of the train. So if you see that the displacement exceeds a threshold of concern, you slow down the speed of that train. So that's the decisions that the railroads make. So instead of telling them, look at the data at the office, you look at the data on the bridge on real time. The student was Marlon Agüero. He programmed everything that you see here. So one message that I give for those interested in augmented reality is 100% about programming. So if the students don't like programming 100%, then they should look for another topic. I will continue, and I hope you interact with questions toward the end. They asked me to keep going and cover the presentation and take questions at the end. If you want to write them on the chat, we can answer them also later. This is a collaboration with Tao at the Chinese Earthquake Administration, where we hit a railroad bridge and wanted to do the inspection on real time with augmented reality. Actually, this is 5 years old video. And this inspector cannot carry iPods, cannot carry iPhones, because they also need to climb these bridges. As I mentioned, I dropped some cameras to the river when I did this bridge inspection. So here we climb the railroad bridge. I use both hands going up the bridge and go to the cross beams, the knee braces, all the through-play gear is a 1/5 scale, and collect this 3D mesh automatically with the headset. And as you can see, this 3D mesh will enable me to create this time machine or deploy my data. Especially, I will show it at the end of the second half of the presentation. We are almost there. How these applications use this 3D mesh for information. We are talking about human cognition. We're talking with leaders in workforce training, development, educational psychology, and scaffolding learning. And we are advancing the training of inspectors so they can accelerate known skills or acquire skills much faster. This is David Mascarenas, my colleague in Los Alamos. We've been working on this since 2016. And this is the HoloLens 1. I have everything now done with HoloLens 2. And this is the application domain where we do all this. The interfaces with the railroad, we have a lot of interest with the Federal Railroad Administration, Transportation Research Board, some of the railroads in North America to assist the inspectors on the field. Safety is the #1 concern, so we are looking into accelerating quality, increasing safety, and reducing time. This is Somi Chavez when she was a senior in civil. She was working in Los Alamos, and now she went back and worked with them. And this is she also worked as a bridge inspector. So she wanted to have this application with Marlon on having a faster inspection. Instead of 30 seconds, it's 12 seconds, even more accurate in terms of the Los Alamos County engineers, and safer because she doesn't have to climb with the tape on the wall to measure these cracks. Another application, this was Fry Xuan. He was a computer science. So it was his idea. He said, hey, we don't want to see numbers. We just want to see a big bubble moving when I move the sensor. And if it exceeds the threshold, it will turn red. So when you work with different departments and different students with different backgrounds, they have better ideas than that you could even think of, and that was his contribution. This is developed by Jack Hanson, Maimuna Hossain, is a mechanical computer science, and also we're gonna do with the new phase on mode shapes in the class. So we're gonna teach this actually this week, modal analysis with the overlay of mode shapes with the structure. This is a lab setup where we have a cantilever beam. You have this first mode at 3 Hertz, and then we have the second mode at 18 Hertz. I'm gonna see this with the mode shapes on the lab. So that's what we're doing here. And then you can see how the pole is indicating a location, and we're gonna try to change that on real time within the second mode here. So very exciting work. In terms of the databases, this work was by Dilendra Maharjan on his master's. We have a SHM article on this access to database. In terms of industry, this is the highest interest, collecting this database, maybe your bridge data record, or maybe your bridge model in the CAD drawing, and updating like a recall of your vehicle when you had to replace your car. The database updates, and you have that on the system, so you could read it with your QR code scanner and overlay in front of you. This is how you have this interface with the physical structure. This is let me bring this down. So Dilendra was working with the National Lab. We're looking on these canisters and how you could measure this information without touching or opening the canisters. We presented this in 2018, and you have these 12 canisters which different information inside. We scan the QR, we send it to the database. The database, we created a socket between the wireless headset and the database. The database could be changed, could be updated, could be improved, and every time that we go to the field and read our QR, the information that we need at the field opens up for us like this. So this is very useful for industry, could be pharmaceutical industry, where you have this amount of changes on the information that you wanna cluster and access remotely. So that was very, very useful. Another application is I will move to the next one, is the eye tracking. So we're using the eye tracking not only to identify patterns, but also to change self-training of bridge inspectors. So you can see how we obtain this information. The eye tracking is not a new area, has been done for maybe decades, but we're using it now in the context of bridge inspection. So I figure this would be of interest for you to see. You have this information on the site, and you can see how you want to get a score of the inspector based on the information that they collect on the elements, the time that they devote for each area, and also you could get a private score that you keep to yourself because you want to improve your information of your inspection. This is the Air Force research where we wanted to explore the collaboration with robots. We've been doing a little more since then, but this is a Baxter robot. They are kind of old school, but we like them because they're a similar size than the human. And we are doing some additive manufacturing for remote fabrication of high quality, low volume of 3D printing. So that was the context of this center. And intelligent manufacturing or intelligent assembly collaboration. This is some of the example of the railroad interface where we go out there with the railroad and collect some of their feedback on. This is a very old bridge that is an example where you want to overlay past inspections. You are not looking for cracks. We'll show that later. You're more interested in taking these measurements on the real time in front of you. This is a collaboration with the New Mexico DOT. They are strong supporters of our approaches, and they are interested in transforming the academic interface to the bridge manual that they conduct for the inspectors. So we're proposing collaboration, again, where the bridge department will dictate which AR they want to see. and we just do whatever they ask us. That's what we are interested in doing. Furthermore, in terms of the robots, this is work by Elijah Wyckoff and Marlon Ball. This is a very simple robot where he was looking initially about this hands-free gesture command. This is with the keys, but then later he's doing it with the gesture. So let me show you on the next slide how we're doing this with the Kinova 3. This is a collaboration with the University of Kansas. They're very interested in fatigue cracks. So we partnered with them to collect this interface of the fatigue cracks on live loading activities with Professor Jian Li. And we went there. This is actually, it's a 2 years project. So this is at the end of the first year. We went there and showed the app on their bridge. This is the menu that we create. We have some upload of the video. The socket goes to the MATLAB. The MATLAB does the computer vision. The computer vision generates the hologram, and the hologram is deployed and anchored in front of your specimen. This is in our laboratory at UNM, where we have this fake crack in a little, COVID laboratory where you have the opening and closing. You send it to the computer make the analysis and generates the hologram or the spatial identification of the features. And then we send that, we create that hologram in MATLAB, then we send it to Unity. Unity transforms those points into holographic values that anchor on this mesh that we create. And this is how it works on the Lawrence. So this is how we did this with them in December. For concrete, we have another project where you could have this combination of AR and AI, and this is kind of the results that we have on the field. This is from different average crack width. This is done by Kade Malek, and we have decreasing on the average width, and then as you can see, the quality of the accuracy is nominally the same. Let me put this here. Again, it's for the inspector to see in half a second the crack in front of them at the site. To conclude my talk and enable some people on the audience to ask questions, I think Eleni, Christian asked me not to take too much time to enable this interface. I have the last few slides is about the future. So maybe that motivates some of you to ask questions here. Some of the work that we have is this with the railroad. We are interested in having this training. This is an indoor facility on the track where we can do some rail gauge measurement. That was something that they wanted to do. And instead of bending over the track and collecting this data, we just do this real-time gauge track measurement. Again, the value is for them to learn faster, but also it can be to accelerate their current ongoing operations. This is a ROS Unity interface that we did with Dilendra, who was taking this class. And again, the Baxter has value for us because it's a human size. We are using the Kinova that I will show on the next slide. In this case, was just to show how we can control the robot by controlling the hologram. So here, you will see in a second how Dilendra is moving the two of them simultaneously. There is a little delay between the gesture and the robot, but basically it will follow with each other. As you can see, similar experience or similar experience than before, but safer, and also coordinating the human understanding or cognition with the robotic interface. We try not to automate 100%. We like the human intervention. So with the human intervention, we believe there is a collaboration, like a robot-human collaboration cobot. This is a recent video. So you can see here how we control this Kinova 3 with the, we like to coordinate the local sensor with the Kinova, and also we're trying to demonstrate how we can control this activity with a gesture only to increase safety. This is a video where we have been doing some of the Air Force collaboration. They are interested in training humans faster in terms of landing their airplanes, the problem is that the engines, when you do some austere environment landing, you break it. You need to pay for it millions of dollars. So we wanted to train the pilot, but also emergency responders without having to suffer this cost. So this is what we did. Some artificial environment around the inspector where you can believe there is in this case, it was an austere landing, but it could be fire, it could be rain, it could be snow. We wanted to do some collaborations for training with extreme situations. It's something we're going to incorporate with Okio Winge as well. Let me go to the next. Toward machine learning and artificial intelligence, we're very interested in this cobot or collaboration with robots, where inspectors collaborate with some part of their value is the cognition, but we remove the automation or the repetition. So we created, this was with David Mascarenas at Los Alamos. In this, we can have automatic hit, wirelessly control, low cost, with classification abilities and inspection ready. So when the humans tap with the hammer to listen for damage, they use their memory and their intuition. Humans, we are not very good for that. So we prefer to give that to the machine. So this is the most sophisticated mechanism I will always make. And it's a crank rocker. I'm very proud of it. I did it with the help of David. And it's a crank rocker where you can have a repetitive, you can hundreds of thousands of hits, same energy, same distance, and collect these sounds, because the machines remember sounds better than humans. This is how it works. And this is how we tested with this crank rocker, a little solenoid. And then the next one is the sound. It's so those hits, we process that data to do a SHM of those hits. It's not accelerations, but computer vision bad sounds. And with that classification, you can see very successful 746 hits. Half of them were for training, half of them for testing. As you can see, the testing exception, region 2 and 3 is very clear. Even region 1, I would claim, is extremely successful. And we use the first two components on the principal component analysis. This was 2016 research. The confusion metrics, as a disclaimer, I would say the first and the last hit should have been removed, because the energy of the solenoid, when you turn it on, this is a very local solenoid, is not hitting with the same power. But we wanted to leave it there just for leaving everything. So even with keeping any of your experiments without removing those first hits, you have a very high level of success. Now moving forward, we created the ground robot. You saw the video earlier, and again, it's a low-cost platform where you can hit on the rocks, and we can inform of the health of your highway. In the Southwest in North America, we have a lot of mountains where we drive through the entire year, and because of the freeze and thaw, the snow, and changes on temperature, we have this covering the road. So we go out there and humans rappel and tap it and see if it's about to fall. So we propose to have this tap testing that informs with this sound that about to fall. And that's Roya Nassimi. She's now in Nebraska doing her postdoc. She was working on this at the end of her PhD. Another futuristic interface is this AR Brutus. So Brutus is the robot. So we provide the human with this hands-free control of Brutus, where you go and move the robot where you like, no joystick, and basically now this is with Marlon Ball in COVID in his house, but now we're looking more towards this dynamics coordination, human and vibrations with real-time response of the human to the activity of the robot. In this case, we were moving Brutus inside the house and taking it close to the area or the surface where he was going to hit. In this case, I asked Marlon to hit the wall of the house like if it was a rock. He told me that was not allowed because of his wife. His wife would not let him hit the wall, but still he got close by and showed that if he would need to, he would hit the wall, but that was not a tapping because we didn't want to damage his house wall. And with the Navy, now we're moving on this underwater interface with moving objects, also with the Brutus on the top, and now we're developing an underwater Brutus for tapping surfaces or structures and classifying damages below water. First, we build on the university swimming pool, and then we go to the lake after we tested. It's not as cold at the swimming pool. And this is the laser that we developed for capturing this underwater activity. This is the Navy students, the cadets, Joshua Marine, Navy, and they really like this research, and they just jump on the water anytime that they can with this platform. This is in Shenroy and Massa PhD students back then. And this is the Brutus operating on the pool. Again, we do it with a control environment. This is the Sea Rapid boat from NSF for a disaster emergency recognition. So we use the same boat with the University of Washington. They came for a few days and they were extremely helpful because, you know, we couldn't have all this boat without their help. So thank you for their help. So to conclude, I just wanted to allow 20 minutes for people to ask questions. I have talked too much. I wanted to share with you new advances in technology that can contribute to objectively inform humans and their surroundings. Again, it's a community-centered, human-centered interface. We talk about new interfaces, human infrastructure. We think that's the future. So for MARS-SHM, I think that's what you are doing, talking about the future. So we believe the future engineer, manager, inspector, owner will be collecting and analyzing data on these interfaces. We are proposing to see, measure, and collect data faster. That enables these changes on decisions on the field. Finally, there are a lot of opportunities. So for those who are interested in this area, I think feel free to contact me. I'll be glad to share, look for collaborations. I think workshops like this one enable us to start new collaborations together, and I'm looking forward to hear those. I thank you everyone for your making time today to attend. I see some friends on the audience. I see new people. Looking forward to talking with all of you. Thank you.
Thank you so much, Fernando. It was a fantastic presentation. You have this background of very, very nice presentation, very thorough presentations of what you do in your group. And I'm sure there are many, many questions from the audience. If the participants would like to ask questions, you can just raise your hand. Or if you cannot, for some reason, you can also use the chat as well. I am going to ask a very brief first question just to make everyone get comfortable with asking questions. I know of some efforts that have used this experience, this immersive experience for technical service, for example, for technicians that go into the site and they don't have to look at the manual anymore, but they just have everything like in their lenses or whatever, and they know what components. Is this something that is already being applied commercially, or is it just in the phase of also research?
Oh, I think commercially they do it sooner than us, but they don't actually do it. So I mean, there is a lot of interest in actually creating this, as you can see, this menu here. Mm-hmm. But I don't know. Again, I'm not working in industry these days. I know this is extremely valuable. The problem is that we actually need to increase the technical components. So creating drop-down menus is not an issue, but for example, to create this crack computer vision with or the concrete have a second interface. That's not that easy. So the menus is not that relatively is the easiest part. We can create menus in a day, but to actually have the technical, for example, you need to know signal processing, you need to know computer science or computer architecture, and you also need to know a structural engineer, or maybe on the railroad, you need to know what the railroads they're interested in, not so much the accuracy, but maybe safety. So it's I think it's a very, very active area these days. So
thank you so much.
Maybe also a question from me, Fernando. Thank you very much for this very nice presentation. When you create these interactive menus, eventually you also get the feedback of the experts, right, or the inspectors, essentially. Yes. And how do you put that feedback back in the loop, maybe? Does it help you redesign algorithms or improve algorithms or adjust somehow?
We change them. Yeah, we change them. So very good question as well. So for example, with the New Mexico DOT, when I presented to them, I create this very nice strain gauge interface with the inspector for the, as I mentioned, for the railroad. I like a strain for fatigue calculation. I think the strain is a very, very valuable information. And they told me, hey, I don't need to see a strain and stresses and micro strains. Show me the concrete crack width at sub-millimeter level. So I just listened to them and I switched my direction and change the speed of my algorithm, remove the wireless sensor and do everything in computer vision. I think it's not exactly what you asked, Eleni, but I think you're asking, can we benefit in the technical design or
even in because you might do, for example, if one application is to identify cracks, right? So I guess you get their feedback somehow on some sort of labels they assign when they click those interactive inputs, I guess. And then I suppose you could use them as a sort of labeling to improve your maybe classification algorithms or other options.
Well, I think I can, I can also benefit from them. So I'll think about that.
But I don't know, of course, to what extent right now it's a closed loop, right? So you might be giving them the tool and then you don't get a chance to have access to their feedback. So perhaps this is not something that's readily available now.
No, we work together. I think they're very nice and very, they don't take the candy and run. So they cannot do it because even you can give them the application and the application needs to be maybe updated or so we work closely with them. They trust us and we listen to them, and they also, they listen to us, but we listen to them. And when they give a suggestion on the crack, for example, on this crack width, we show it to them and then they say, hey, can you do it with an angle? Because I don't want to look perpendicular to the surface. So we just put the angle on the algorithm.
Yeah. There is a question by Ayan, I guess. You could unmute yourself. Yeah.
Hi, Eleni.
Hi. Good.
Nice to
see you. Hi, Ayan.
Thanks for making this workshop. And hi, Fernando. Excellent talk.
Thank you, Ayan.
And we already started a bit of collaboration, and I see there is a huge potential with this area. So I have two simple questions. The first thing is related to the sensitivity of the device. So, we are going to take the real-time measurements, but do you see any kind of specific limit that the measurements can be taken? Like, for example, what we see with the device sometimes that if we are too far, then the hologram things doesn't work properly and it doesn't give the measurements very accurately. So we have to be with some certain distance. So do you see that kind of sensitivity can be improved with the device, or this is the limitation of the device, and unless we have the next generation HoloLens, it's not possible to?
So thank you, Ayan. You know about the challenge here. So I I will comment for people on the audience. There are three ways to look at this problem. Number one, we need to agree or accept or want for the human to be close to the structure. So that we need to agree on that. If we agree on that, the headset enables that inspector who is close to the structure to collect the information. It may be that was not clear, but we need to agree that we are trying to help that human who we agree needs to be close to the structure. The second one is that, hey, it could be that maybe instead of using the camera on the HoloLens, we use another high precision camera. It could be a different kind of feature. It could be temperature. It could be other level of sensitivity than the camera on the HoloLens is not designed for. You could use some fusion with maybe sound and camera and connect that hardware to your wireless socket. So you could also use another camera. The third one, you can also connect your HoloLens and say, you know what? I need to be nearby, but I don't want to be remote because I don't want to do this a mile away, but I want to be 20 feet. 20 feet is the distance that limits your meshing. Let's put it for anchoring if you want to anchor. So then you could create this, not human, super close, but relatively close. You could put your camera on the drone. You can put it in your robot. Doesn't need to be on your shoulders, or it doesn't need to be on your headset. Okay,
so some sort of fusion with other sensing devices probably increase the breadth of the measurement. My last question regarding a very basic training experience. So for a typical civil engineering, say undergraduate students, what kind of things do you expect that they should be enabled to do this kind of thing? Because this is going to be one of the challenge for us to engage more civil engineering students in this high-end technology. What kind of things do you envision? Do you think we should incorporate more related courses in undergraduate curricula such that they are well prepared? What is your vision on that?
So this is a class with civil engineers, and what I do, I take them to the field, to the sensors that they build, and they need to measure the structures on campus, and they love it. They love it. So I think the younger generations, they are way less conservative than we were. So we need to actually push a little harder than, it's not, they are ready. In terms of what we can do for them, is more about go earlier to the middle schoolers. We have a project with the railroad now where we're trying to recruit talent, not in high school anymore. Forget about high school, it's too late. They already want to be medical doctors or lawyers, or if there are any of them on the audience, it's too late. So we need to go to the middle school and get these sharp boys and girls in middle school and tell them, this is an important problem on society. You need to actually be the one who create the new civil engineering. After 300 years, now we're going to do a new civil engineering. So you have to invent it.
Yeah. So more outreach to school level
earlier. Yeah. And also bring them to your lab. Ayan, I think I've been very successful with these high schoolers. They program Unity. They do the video games already, so they are 15 and 16. They already know how to program AR. And then they stick around. I have, let me see. I kept one high schooler with me who is now finishing the master's, for example. So, I mean, they also go to other places, which is good for them too. So nothing wrong with that. But, and also the younger inspire the older students in your group as well.
Yeah, that's true. Excellent. We'll chat you later. Excellent job. Thank you so much.
Thank you.
If anybody has an additional question, we still have some minutes for
I don't see a question, but maybe let me ask this because I'm genuinely interested. You know, ever since the first time we met, Fernando, you always were, you know, part of the group at Illinois where there was a lot of hands-on work with sensing. So I was wondering, is this something you think we should adopt? Research groups, you know, working in SHM, does it pay off to really also have some in-house expertise on some custom solutions? This is what I understand from what you described. Or is that something we could also maybe try to find through collaborations?
I think it depends on the personality of the director. Like you are using many things in your group that other people don't use. I think the interface with the data, or I mean, you can call it augmented reality, mixed reality, or LiDAR, or point cloud. I think. Well, in particular, I think we should adopt it. I think, especially because, you know, even this was even before metaverse and Facebook and all that. And Facebook, they say we are not a social whatever, I don't know what they're called anymore, platform anymore. We are an augmented reality platform. So if we don't listen to what is happening around us, it's up to us. But I think we're going to lose in the reality, the opportunities. Like the next 5-10 years. Will be, so the sooner we jump in, the better. So yeah, if anybody wants to team up, I am available.
And then I also will remind everyone that you do offer this course for the IMAC typically, right? Is it every year that you repeat it?
Yes, so we hope to do it in 2023 for the low cost. I mean, it's basically building the sensor, but yeah, we'll be offering this also. I mean, I hope the APSS also come back and we do it again there, and we already presented in 2019. So yeah, I hope, you know, more feedback from people. We can also find a new direction, right? We are just starting here, so it doesn't need to be what we show here today, but if there are new ideas, we can move on that direction too. So Eleni, if you have ideas, let's go for it.
Yeah, sounds good.
Yeah.
Maybe we ask the audience for any last questions they would like to ask to Fernando.
I have a quick question regarding the course, actually. Are these courses, is there a possibility of the information of these courses being shared remotely with other country universities, for example?
We can. The difficulty is that, you know, because we build a sensor, there is some hardware that needs to be enabled.
Right.
We could do it too. We actually, last year we did it with Zoom because my students were here, but I couldn't see them. So we did it with Zoom, but I met them in parking lots, or, you know, I opened my trunk and I gave them the little Tupperware with the sensor. So yeah, that can be done.
Okay, that would be nice.
With this, I think we're right on time. So what we typically do is we ask you, Fernando, to close with a statement of what you would like to leave us with, a message.
Great.
Or.
Great. So, well, thank you everyone for coming today. I hope this workshop enlightens new collaborations and sharing all we have to offer, and also helps us an opportunity for 2022, 2023 that is opening up. People can travel internationally, and looking forward to see everyone in person soon.
Good point. I give it back to Christian for announcing our next event.
Thank you, Eleni. Thank you, Fernando, for this fantastic presentation. I would quickly like to talk to you about the next presentation. We're going to have a presentation 1 month from now on April 25th. And actually, this is going to be a special presentation, or a special day, because we're going to have 2 presenters that day. We're going to have Professor Chulmin Yam from the University of Waterloo talking us about vision-based structural health monitoring techniques, and Professor Wei Song from the University of Alabama that is going to talk to us more about hybrid simulation and their interconnection with the structural health monitoring. So please do check out our website, and if you're interested in these topics, make sure you register so you can receive a reminder shortly before the conference. With that said, thank you so much for being here, and I give the talk back to Eleni so she can close it.
Yes, thank you, everyone. Especially thanks to Fernando. And as everyone mentioned, let's hope to meet soon, preferably in presence. Bye, everyone.
Take care, everyone. Bye.
Bye.
Bye, everyone.
Bye.
Hey, sorry, I let this here. Thank you, Lenny, and I don't know if you hear me. Hold on.
Yes, now I hear you. I just wanted to say goodbye, but thanks a lot, Fernando. It's very nice presentation.
Thank you. We'll talk soon. I'll shoot you an email.
When you want. Yeah, exactly. I'll wait to hear from you. Bye.
Very good. Bye.